course. Today we're going to talk about multi-agent programming in Erlang. And last week we saw how to build multi-agent systems. It's kind of complicated because messages can go all over the place. And we used port objects and active objects in RS for that. But there's actually an industrial system called Erlang, which was developed in Sweden a long time ago, and which does this very, very well, very efficiently, and with very good fault tolerance. Okay. First, a few seconds to think about the Ukrainians who were fighting for their freedom and for our freedom. So, today I really want to talk about Erlang. So I'm going to show you a lot of stuff about Erlang and why it's really a very system with a very good fault tolerance. I'm going to first give you some kind of refresher. We actually saw already a small introduction in Erlang in a previous course, but I want to say much more today. I really want to go into the details of how it works, how the supervisors work, how the generic behaviors work. So I'm going to show you some of these patterns, the tools, the stable storage. The supervisors and the stable storage are working together. I'm going to show you how to build a generic server, how Erlang does a generic server, and I'll show you some neat techniques for avoiding race conditions for when you do multi-agent programming and doing asynchronous and synchronous calls. I'll show you how to build a supervisor. A supervisor is the Erlang thing that handles fault tolerance. Okay. So a very quick overview of Erlang to refresh your memory. It was developed by Ericsson, a Swedish company for telecommunications, a long time ago, 1986. So it's actually even older than Java. And it is released as a platform called OTP, Open Telecom Platform, up until today. And there's a team in Ericsson maintaining it up until today and extending it. There's also a community and an organization called the Airline Ecosystem Foundation that organizes the whole community and mutual support and all developing things in Erlang. And you can download Erlang for free. It doesn't have any kind of fee attached. Erlang is multi-agent. The programs are very lightweight. They call them processes, but they're like threads. They're very lightweight. They're called processes because they don't share anything. The principle is that there's no sharing. And that's the main difference between port objects in Oz and Erlang processes. Each process is a complete thing. There's no pointers across, okay? No sharing. All data is copied. And you might say, well, that's inefficient. Actually, not so much. It's actually very cleverly done, and the processes that are on the same computer, sometimes they do share in implementation. But semantically, they don't share. And if they're distributed, they don't share. That is really important for fault tolerance, because if one process fails, it affects nothing else. Okay? Also, there's messages, and it's not like a stream. It's different. Erlang has a mailbox. They call it a mailbox. And the difference between a stream is that you can receive the messages out of order. So if I send messages 1, 2, 3, I can take message 2 out without touching messages 1 and 3. And that's very important because of the pattern matching, you can do that. And that lets you do some very good programming patterns. And Erlang is supporting very long-lived, robust distributed systems. And they have a very interesting philosophy called let it crash. And it's kind of strange because this works very well, and so Erlang is much better at doing fault tolerance than systems like Java and so on. So it's kind of strange. Why is this technique not more used? And it's mostly because of legacy. I think that shared state concurrency is kind of the legacy approach, but the Erlang no sharing, let it crash philosophy is actually much easier and better for fault tolerance. Okay? And one of the examples is, so Ericsson makes telecommunications equipment. They have this ATM switch called the AXD301, which has 1.7 million lines of Erlang inside, and their marketing department claims 99.9999999% availability. That's kind of a very extreme claim, because that would mean, so there's 9 nines here, that would mean that every year, over 1 year, the system would only be down for 30 milliseconds, okay, per year, because a year is 30 million seconds. That is kind of unbelievable. Probably there's too many nines here, but it's still an extremely highly available system because of the way the Erlang organizes it. And we'll see how that works. So Erlang is by far the system that lets you build more reliable software. By far. If you want to build reliable software, it is the best system, okay? In the slide, I have some bibliography here. If you want to understand more about Erlang, Joe Armstrong is one of the main inventors, and he has a book on programming Erlang. There's also a book on designing for scalability with Erlang by Francesco Cesarini and Steve Vanoski, and a really good website for learning it is called Learn You Some Erlang for Great Good by Fred Hebert, but there's other stuff. There's a huge amount of documentation on Erlang. Okay, but let me first show you some graphs to show you the kind of performance that Erlang gives you. So here's a graph that shows process creation. So a process in Erlang, it's like a thread, but it's no share. So in that sense, it's like a process, because it doesn't share, but it's lightweight like a thread. And here's the number of processes, okay? And here is the microseconds, how much long it takes to create a process. Now, the red curve is Erlang. And this was actually a graph done by Joe Armstrong in 2002. So probably you can multiply these numbers by 10 today. Here you have Java and C#. You see that the creation of a process in Java and C# it took in those days a couple of hundred microseconds. And you can only go up to 1,000, couple thousand, and then it doesn't work anymore. Because actually threads are very heavyweight in Java. You can't have so many of them. In Erlang, this graph starts at 1 microsecond, but up to 2,000, a little bit more than 2,000, the time is so low that it's even below this graph. So here it started at 2,500 approximately. It takes a few microseconds, but still less than 10. And in this Erlang system, it went up to 30,000 processes, okay? So you can see the creation is much cheaper in Erlang, and you can create many more, okay? That's for the creation. Now the message send, I send message to a process. How long does that take? Okay. Now Java and C# are not really made for that, but if you do message sending in those languages, it takes several hundred or even much more thousands of microseconds. And C# it would take things like something like 50 microseconds. In Erlang, it's even up to 30,000 processes, it's less than 1 microsecond, okay? So today, probably you can multiply these numbers by 10, and these numbers, you can probably divide them, but the relative position is the same, okay? So you can see message sending in Erlang is very cheap for a large number of processes. So the mindset in Erlang is processes are usual, are normal things, and you can have many, 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 many of them. So don't worry about creating them. Okay? Here's a web server. Here, the number of processes. So this goes up to 90,000. And here's the throughput. So again, this was measured by Joe Armstrong in 2002. You can see the throughput. So this is in kilobytes per second. So the red is Erlang. It's a system called YAWS, yet another web server, running on Erlang on NFS. Green is Apache on a local disk, and blue is Apache on NFS. So NFS is a network file system. Notice Apache doesn't handle so many. I mean, it stops here. It's still a few thousand. That might be like 4,000. You can say, wow, I can create 4,000 processes in an Apache web server. But in Erlang, that's nothing. And if you have a web server that's highly overloaded, 4,000 is really not so much. So what happens is, if you overload the Erlang web server, the performance can go down. You can see it goes down a bit, but it doesn't crash. Okay? So Apache will crash at around 4,000. YAWS will still give you 800 kilobytes per second up to 80,000 processes. So you can see Erlang is very robust in handling large number of processes. It will not crash. It will keep going even if the performance goes down with the overload. Okay? So again, number of processes, is a process, very normal thing. Okay, here's the AXD switch that I mentioned before. So there's an article about it by Ofliger, who's one of the developers in Ericsson of this switch. So this is an ATM switch. So ATM is a kind of a connection-oriented protocol used for telecommunications. So the AXD301 is like a very big, robust ATM switch. And it's written, well, here they say it's 1 million lines of Erlang. It also has some C, C++, and a little bit of Java. There's also the Erlang OTP underneath, which also has Erlang in it. But if you see here, this is very interesting graph. On the horizontal line, you have what's called offered load. This is the number of attempts to make a connection, to make a call. It's telecommunication. The number of attempts. So there's assume that the system is made up to, this is normalized, 100% is the maximum, is what it's designed to do, the maximum. And here is the actual throughput of the calls that are accepted, okay? Here are the ones that are attempted, so offered load, and here are the ones that are accepted. So you can see up to this normalized 100%, they all will be accepted here, okay? But if you keep overloading the system, you have, so that's the real problem. Huh? In big systems, it's easy to make them work for a long, small load. What happens when the load is very high, when you overload, everyone is trying to make a call? What happens? Does the system just crash or what? Well, in the AXD301 case, you can see that this is the maximum throughput, but if you increase the offer load 150%, it stays the same, but if you increase it even more, 1,000%, so you try to make 10 times as many calls as the system can accept, what happens? The throughput will go down, so the number of accepted calls goes down because the system has to use some of its resources to explicitly reject calls, okay? It has to handle them. So that, it gives you this yellow load, the handling of the rejected calls, okay? So all of these calls are rejected, of course, because you can't follow this line up. This is the maximum that the system resources can give you. But you can see it gracefully degrades. It does not crash, okay? So it has, the throughput drops linearly, pretty much, when overloaded, 40% throughput at 1,000% sustained load. Okay? So that's a very good behavior for a system that has to work in overload in any situation, so for real-world systems. Okay? So this is the kind of thing that Erlang can do. And remember, the system is very highly available. It will not crash. Okay? Available means that the probability of the system being there and able to do something at any given time is a very high percentage. It may not be 9 nines, but it's very high. This is a very highly available system. So this is one of the best ATM switches that exists, okay? And it was written in Erlang. It's from Ericsson. So that gives you some ideas of what Erlang is good for. Now, Erlang is also used for regular other things, and I'll talk about that. I'll give later, after this technical presentation today, I will give another presentation, which is given by a game company engineer who uses Erlang for maintaining the infrastructure of massive multi-user games. And there's many large games that are using Erlang behind the scenes. And for example, one of the big ones is Call of Duty. So all of the Call of Duties are using a lot of Erlang behind the scenes because it has to keep going even under high overload. Okay, so that gives you kind of the motivation, what Erlang is good for. Now I'm going to refresh Erlang concepts, but then we go and I'll explain where all the real good parts. How does Erlang handle the fault tolerance? First, a refresher. So Erlang is multi-agent language. Each process, inside a process, it's purely functional. So this is it's like kind of like a port object. So it's essentially a recursive function, and whenever it reads a message, it will do a recursive call. Okay? The variables are single assignment, so it's actually very similar to port objects. Okay? You can also pass functions as values, so it's lexically scoping higher order. So inside the process, it's a pure functional language. Okay? It has pattern matching. The pattern matching is more sophisticated than what we saw because of the out of order, and I'll explain that later. Erlang is also a symbolic language. You have symbolic data structures, integers, arbitrary precision floats, atoms, but also symbolic lists, tuples. So the syntax is a little bit different from what we saw. So the lists have almost similar, they have commas. The tuples use braces, okay, as a tuple. Strings are lists of ASCII codes, and it has an extra one, which are binary vectors, and this is important. So it's bit vectors of different lengths, and this is so you can implement network protocols. Okay, so you can do even pattern matching on binary vectors. Okay, now a very interesting topic: dynamic typing versus static typing. So first of all, Erlang is a strongly typed language. What that means, so there's two kinds of languages, strong type and weak type. Strong type means the types are enforced by the language. That you cannot break the type scheme in a program running in the language. And many languages do that, of course. Java, Steam, Haskell, and Perl are all strongly typed. But there's also weakly typed languages, and the most famous ones are C and C++, where you can use casts to basically look inside the internal representation. So that's very weak, and it doesn't let you proof very much. Okay? So Erlang is strongly typed, which is basically, in my view, the right way to build it. Now there's two ways to do strongly typed. You can either make your language dynamically typed or statically typed. In a dynamically typed language, you only know the types at runtime. You can assign a variable to entities of any type. Basically, there's only one type, in a sense. So a dynamically typed language is like a strongly typed where everything is inside one type. So you can assign variable to any entities of any type. But then you also have statically typed languages where you declare types at compile time, and then the compiler enforces that you will only assign variables of the right type. Now, static typing, it seems to get a lot of good press, It allows catching more program errors at compile time, right? The compiler will see if you make type error. But actually, it's very curious. Statically typed languages, programs in them are not more resilient. They actually, the errors that you catch are kind of surface errors. They're basically mistakes. I call a function with the wrong kind of argument. But real deep errors, errors in the logic of the program, are not caught, okay? And it's very interesting because Erlang, being dynamically typed, is much more resilient than any other language, even statically typed languages. So a statically typed language like Haskell would claim that the static typing helps a lot for the robustness, but there are no distributed, long-lived Haskell programs, okay? Unlike Erlang, okay? You would not build a long-lived, robust system in Haskell, but you would do it in Erlang, and it works very well. So basically, the difference between dynamic and static type is kind of like a red herring, which means it's actually not so important for resilience. Okay? There's a lot of argument. You will hear lots of religious wars between those two guys, the two communities, but actually it doesn't make so much difference. The real importance is that your language is designed to handle failure and do the right thing. And that is not related to typing. That is a conceptual thing. So Erlang does that, okay, and lets you build very robust programs, okay? So that's one thing. So Erlang is strongly typed. Erlang is a very classical language. The source code is organized as modules. So it's not really very sophisticated, huh? So a module is like a file. It exports some function declarations, some declarations, and it will import. It may need other modules. So here is a module math, which exports this area function, okay, which has one argument. So you have a list of exported function. It also imports from another module called lists. It imports a map function with two arguments. So you basically have a dependency graph of modules. So that's very classical. There's nothing very sophisticated going on there. Okay, so that's the basics of Erlang. Now we go more to the multi-agent things. Okay, so message passing first. So an Erlang program consists of processes, and you can create them easily. Any process can create another by calling a function called spawn, where the argument fun defines the behavior of the function. So this may be some kind of recursive function that defines the behavior, and the process ID that it returns is kind of a constant that identifies the function, the process, and you can send messages to it. Okay? So here you can put anonymous or named functions. So PID is a unique constant. And you can send messages using this notation with an exclamation mark. Send message to process ID. Okay? And in order to know this process ID, you have to, either I create the process or somebody has told me what the ID is. You cannot forge them, create them. Okay? And messages are sent asynchronously, and all the data inside here is copied. The process that receives it will get a copy, which is identical, but it's a copy. That means if there is a failure, a hardware failure, then the copy will still exist, for example. And it's asynchronous, so it's very similar to ports in that sense. And the messages are received by a statement called receive, the receive statement. And this one it's more sophisticated than streams and port objects, because there's a special concept in every process called a mailbox. Okay? And the mailbox contains an ordered list of messages. So it could either be empty or you could put message in there. They're ordered in order of arrival. But you don't have to extract them in order. So if I have a bunch of messages in the mailbox, I can take out one in the middle, okay, if it matches the pattern. It's not like streams and port objects. So the main difference is, in a stream and a port object, the messages are read in the exact order in which they're sent, whereas in receive, you take out the first message that matches and the others stay. Okay, so they stay in the mailbox in order, but you can extract them out of order. And the receive statement uses pattern matching for that. And this is conceptually very similar to what we saw in Oz. You have a pattern, show a symbolic data structure, but you can also have Boolean functions, a guard, and you can have a bunch of patterns. So this receive statement has a specific kind of semantics that I'll explain in a minute. Okay? So basically, it's like this. Send, PID, you send message, and receive, you receive here, and you have a pattern here, patterns, and some actions. And you can also add a timeout. So if the receive can also say after 50 milliseconds, and there's no messages, do something. Okay? So that's basically how the send and the receive are written. Now, I have to say something more precise about the receive semantics. Okay, because it's not like a stream. When I execute receive as a statement, if the mailbox is empty, it just blocks. Okay, that's reasonable. It waits until there's a message. If the mailbox is not empty, it takes the first message. So there's messages in order. Takes the first message and tries all the patterns in order, starting from the first. If it finds a matching pattern, it takes the message out and executes the code. And it does that for all the messages. Okay? If no pattern matches for any of the any messages that are in there, it blocks again and waits for another message. Okay? And any unmatched messages, they stay in the mailbox. They just stay there. So it's kind of like a mailbox in a human society. Yeah? I take out the things that I'm interested in, and maybe I leave the junk mail in the mailbox. Okay? It's removed by someone else later to put in the trash. So you can have multiple receive statements taking out different kinds of messages. So that is important for modularity. Okay? Different parts of a process can treat different kinds of messages. And you can remove them out of order. Okay? So you can do multiple things in a process. You can actually have multiple things going on, even though it's one thread, and one part of the process will handle certain things, and the other part will handle other things, and they will not be conflicting with each other. Okay? So that's very nice. There is one problem though. You can have memory leaks, of course. If you leave a message forever in the mailbox, it will consume memory forever. So you have to be careful that messages don't stay in the mailbox forever. Okay? And the patterns are just symbolic data structures, very simple, similar to Oz, with variable identifiers and Boolean tests. Okay, so that's how the receive works. And later you see when we use it in the examples. Okay. Now let's go on. There's more abilities than just spawn and send receive. There is something called process registering. A PID is just some kind of constant, but maybe I want to give a more significant name, a name that means something to the process. So I can do that using register. I can register that the PID corresponds to some atom, some symbolic atom. And then I can send to that atom, and it knows within the computing node, this correspondence is maintained. This is important because I can keep an interface unchanged even if the process crashes and it's restarted or if when you restart it, it will have another PID. But the atom that it registers with can stay the same. Okay? And you can also unregister, of course, and you can also return the PID of a registered process. okay, and find out what are all the registry processes. So this is important for maintaining an interface, okay, to processes. Okay? Okay, that's interesting. So that already, we start now to move toward failure handling. Now I go to the main concept, the main primitive concept that's used to build failure handling. This is called process linking. This is the main primitive operation that Erlang uses to build fault tolerance. Okay? The idea is very simple. Two processes can be linked together. So there is a conceptual bond between them, and you can do it asymmetrically. So any one of them, PID1 will call link PID2, or opposite. But the link is symmetrical. Okay, it's bidirectional. It doesn't matter which one creates it. Once they're linked, it's a symmetrical connection. And the linking the meaning of it is what happens when there's a failure, or when a process terminates. When a process terminates, it sends what's called a signal. So I'm not saying it's a message, not yet. It can become a message, okay? But it's a signal. So when a process terminates, there's a reason for the termination. The reason might be normal termination, or it might be a crash. So the system will, if the process terminates abnormally, let's say there's an uncaught exception, or maybe there's a hardware failure or something, the process fails, then you have another reason, another signal, and the exit reason will be some tuple where you have some reason here, and then some information about the state of the stack, okay? When there's some kind of runtime error. So normal or not normal when there's an exit. But when you exit, there's some reason, okay? Now, these signals are propagated through all of the linked processes, okay? Now, the linked processes actually are a set. If I have two processes linked together and a third one links to the second one, in fact, conceptually, they form a set. Because the linking, the transfer of the signal is transitive, okay? So all the linked processes in a connected, that are connected together, that have some connectivity, is one set, okay? Called the link set. So this is transitive propagation, okay? And the default behavior, when nothing is done, is the link set. When one of them fails, they all fail, okay? When a process receives an exit signal with reason different from normal, so it receives a signal, that means the linked process failed, and it's abnormal. So other than normal, it also terminates. So if any of the processes crash, it forces all of them to crash. So it basically maps the failure of one to the failure of all of them. Okay, so you think that's kind of a very, very strong thing to do, okay? Maybe you have 100 processes linked together and one of them crashes. Well, you force all of them to crash. So basically you map the failure to some global failure state, simple failure state. So that's the default behavior. Okay, so the link set is basically making failure common, making failure, uniform failure for all the processes. That's the default behavior. But now you can change that default. If I'm linked, if there's two processes linked, I can actually change my behavior. There's a flag called track exit flag. If I set that flag to true, then the signal is transformed into a message. And then I will not fail, okay? So there's two possibilities, huh? So if I have two linked processes here, P1, P2, If this one fails, then the other one will also be forced to fail. That's the first thing. But the second possibility, here I have the trap exit flag. If this one fails, then there is a message sent to the second one. Okay, so there's two possibilities, but only if the trap exit flag. So the default is all of the linked processes will fail, okay, together, but not if you send a trap exit. Okay? In that case, the exit signal is transformed into a message which is sent into the mailbox of the other process, which receives it normally, and it can handle it. So you see, in the second case, the process P2 is actually observing. It sees the failure of P1. And this is how you build supervisors, okay? All the worker process will stay in the first situation. They're all linked, and they're like a pool. And supervisor processes will be observing them using trap exit, and will see if there's any kind of failure behavior, okay? So this is this is how the supervisors of Erlang are built, using this primitive, okay? So you don't need any other kind of magic. This is the magic, and this is supported by the system, okay? Now, if you know something about distributed systems, you will see that detecting the failure of a process, it's technically, it's what's known as a perfect failure detector. That means you will always detect, without mistake, the failure of a process. So Erlang is actually made for systems that are tightly coupled, like clusters. Okay? This is actually much harder to do for open internet. And in that case, Erlang has to do maybe something slightly different things. So the supervisor trees will be used more like in clusters where the nodes are all tightly coupled and you can see for sure when there's a failure on. If you understand for distributed systems, there's two kinds of failure detection. There's the perfect failure detection when you can always see that a node fails, but that's only possible if the nodes are close together. If the other node is far away, maybe it's in Japan somewhere and there's a network connection to it, it's kind of much harder to see what happens with that other node, and so you don't usually have that kind of perfect failure detection in the open internet, okay? But Erlang is designed by default where you can actually see the failures, okay? For building robust things. This is very fine for cluster or even cloud systems. For example, if you have a cloud database where you have a bunch of nodes sitting in a data center and they're all connected together and they make one big database, and then if one of the nodes fails, the others will see it, the processes will fail, okay? And so this is a good use case for Erlang. And there are databases, cloud databases that use Erlang. Probably the most famous one is called Riak. So there's a number of very big cloud databases. So Riak is a major cloud database, but it's written in Erlang. And it's used for very robust, long-lived systems. So just to give an example, so the Danish healthcare database, so the national database in Denmark, which connects all of the patients, so all of the citizens, all of the pharmacies, all of the doctors, and all of the hospitals, is written in React, runs in React. So this is based in Erlang. So this is an example of a big Erlang application. So this kind of system is built on top of linking, okay? When a process terminates, when there's with a runtime error, you can see that. The system can see that, okay? Okay, so here's a little example, process linking. So if process, for example, it throws an exception inside the process that is not caught, divide by 0, and there's nothing done, then the process will terminate abnormally, and the exit signal is linked process is sent to all linked processes. So here, for example, is a process where the trap exit flag. So I create a process with this function go. I set the trap exit flag to true, and then this loop is the core, is the process loop. This loop is going to do a receive, and it will receive messages for all of the linked processes that fail. Okay, so this is like a supervisor process. Okay. And then, of course, there's a few extra functions that I'm not going to say so much. You can actually send an exit signal without terminating. So this is needed sometimes when you implement supervisor trees. You can also send an unstoppable exit. Maybe the supervisor itself something's wrong and I want to kill it. Well, then I can do that. Okay, so you can actually have layered supervisor trees. Okay. Okay, so that's the basic operation for building fault tolerance in Erlang. There is a variation of it called monitoring. That's just an asymmetric version of linking. Okay, so this, in Erlang, this has nothing to do with monitors in shared state concurrence. Yeah? It's an Erlang terminology. So monitoring is just an asymmetric version of linking. Sometimes you don't want the linking to be symmetric. If you have a client server, if the server crashes, you want to kill the clients. But if the client crashes, we do not want to kill the server. So maybe the client crashes, but the server can keep running because there's other clients. Okay? And we can do that using monitors. So sometimes you want the linking to be asymmetric. Okay? So PID1 can execute monitor of PID2. If PID2 dies with some reason, then PID1 will get a message, but it won't crash. So monitoring is just an asymmetric version of linking. Okay? So that's the basic idea. Now, an Erlang system can be distributed, which means it runs on multiple computing nodes. So you can have an Erlang system running on a single computing node, a multi-core processor, for example. But you can also have an Erlang system running on multiple of these nodes connected together. So you have a bunch of Erlang runtime systems. So these are called nodes, okay? And when you do message passing, you can't tell. If I do PID, if I send a message, I do PID, I send a message M, I cannot tell whether the process is on the same computer as me or somewhere else. So it's transparent, okay, when using PIDs. And I can also spawn a process on another node with a version of spawn which has the node identifier as an argument, okay? Registered, remember registering? That's local to a node, okay? That's in one node, okay? Now, the Erlang system will automatically make connections, like TCP or other kinds of network connections. The first time I use the name of the node, the Erlang system will try to connect, and they're made transitively. So by default, Erlang is a fully connected mesh. So every node is connected to every other node. So again, that's not so scalable, because that means you have order n squared connections. So if the number of nodes goes very high, it kind of goes up too fast. So this is, again, it's designed for cluster computing. And if you want to use Erlang and Open Internet, you have more recent versions of Erlang allow you to change this so it's more scalable. Okay. But for a system like the AXD301, that's actually running on a kind of cluster and with multiple processors. And there you have a fully connected mesh, because that is the most robust one, okay? When I have two nodes connected directly, it doesn't matter if other nodes fail. It's only the failure of the two nodes. So again, it's made for robust systems running in a cluster. Okay? And now a final thing, before we get into fault tolerant stuff, is the dynamic code update. Okay? An Erlang system is made to never go down. And usually the reason usually for a system to go down is that there's crashes, okay? So the Erlang supports that. It has supervisor trees and so on to keep running. But there's another reason for systems to go down, is that the software is updated. And that also cannot allow the system to go down. So this Danish healthcare system, for example, it cannot go down. Because if it goes down, people can die. If I need medication and the database is down, I won't get it. The pharmacy will not give it to me, or the doctor will not be able to connect. So this system is not allowed to go down, even when the software is updated. Okay, see, that's the second reason that you have to support that. So this is a thing called dynamic code update. We want to change the code, new version, without stopping the system. And many systems are not supposed to be stopped, okay? Of course, in biology, that's very normal. An organism never stops, okay? It keeps running forever, during its lifetime, okay? So here's an example, X2000, satellite control system. But there's many examples of these kinds of programs. Even for gaming, if the game goes down, millions of users can be unhappy. And unhappy gamers will stop using the game and use another game. So that's not, but the companies don't like that, so it has to keep running. So how do you do that? How do you do dynamic code? How do you update the code? So Erlang has support for that. So first of all, this is the no sharing is very important here. That means if I change part of the system, I know the other parts will not be affected because there's no sharing. So you see, no sharing is also important for this, huh? And the support that Erlang has is that each module in the system, so in the virtual machine, there can be two versions of the code for each module, okay? And when you create a process, you will automatically be linked to the latest version. But a running process, one that's already running, can still be using the older version, okay? And if the code is changed, then a process can choose which version it wants. So basically, this allows the program to manage the update. You can update, and then the actual running processes will keep using the old code, and then at some reasonable time, you will tell them, now you switch to the new code. You can't just force them to switch at any time. Huh? For example, it's a connection for a telephone, so it keeps using the old code, but when the connection is done, the next connection will be using the new version. Okay? So you can update all of the concurrent processes at the right time because you have the two versions. Okay? So here's a code example. There's syntax support for that. Here's a loop that receives a message and does a recursive call. Okay? So this is the receive. It takes the message from the database. So this is the message. Okay, this should be a brace. And so it calls the function f. So the function f is part of the argument here, and it keeps going. So this is just part of the code. Huh? Now there's two ways to do it. If I just write it like this, loop calls loop, it will use the old version. But if I say in module m colon loop, that means use the new version. Okay. So that means a running process can decide when it wants to switch from the old version to the new version. So the idea is when you update the version, you first update the modules, and then you tell all the processes, now when you are ready, please switch to the new version. And when they are ready, they will switch, and they will inform me. And when they all switch to the new version, then I don't need the old version anymore, okay? And then, so you only have 2 versions, not 3, yeah? 3 would be too complicated. So you have a kind of a transition protocol between the old and the new version. But during this, the code will keep running. Of course, the software has to be written in the right way, huh? The new version of the software has to be compatible with old versions that are running, okay? You have to, at least during the time that they're still running. Yeah? Question?
So, if I understand correctly, if you only use old version calls and you update your program with the new version, it will never get updated.
You are correct. If you only use old version calls and you update, so that means your program, so this mechanism, the 2 versions, it doesn't solve the problem. It gives you the ability to solve the problem. So the program has to do something and it has to switch. So at some point you have to do one of these calls to switch over to the new version. Okay? And once they're all switched to the new version, then you can get rid of the old version. So I'm not giving all of the details, but basically the program has to be written in kind of a compatible way. Okay? But this is done using what's called the behaviors. So the way it's done in Erlang is that the developer doesn't have to do all that tricky stuff. All the tricky stuff is inside the behaviors. We'll say, see. So there's like generic things. If I want to make a server, there's a thing called genserve, generic server, and all of the things, even the updating is handled in there, all the tricky code. So I only have to give the functionality. But this is the basic mechanism, okay? Yeah?
Second question. I forgot.
It's okay. When you remember, you can ask. Okay. I'm only giving part of the details here. Huh?
Yes.
Yeah? You have the question?
If the new version has a failure, so when executing the new version there is a failure, does Erlang roll back to the old one or it just crashes?
It just crashes.
Okay.
Yeah. So then it's up to the supervisor to, when it restarts, it may say, then the supervisor will decide. So if there's a node crashes, the supervisor process will be notified and it decides what to do. Maybe it says, I restart, and in that case, it decides which version it has to use. Okay? So then it knows more. The supervisor has more information. So you have all these worker nodes, and the supervisors are sitting on top observing them. And when the worker nodes crash, the supervisor then decides what to do. So I'll show you after the break how to write supervisors. But real supervisors, I'll show you a simple supervisor, but the real supervisors, of course, it's kind of very tricky code. It's only written once. It's part of the Erlang library. Okay. So one more small thing. So this is a system support. Huh? So the virtual machine supports 2 versions of the code. But you can also do some update in fine-grained way without system support. So I want to mention that too. Using only higher order, of course. You can also do update. If I want to update this server here, so this server ability is this function. And when I do the server, when it receives an RPC, so this is an RPC message sent here, it will run this function with arguments, okay? Now, I can also have another message called new fun, which replaces this function argument by another one, fun1. And so the server, I can actually update it using just higher order. Notice the underlying module code is not changed here. This is a more fine-grained thing, yeah? So I can actually, in a fine-grained way, change the functionality of a process without changing the code. So this is independent of the previous one. Huh? So this one, the previous one, is actually a heavy-duty one where the whole system is changed. But if I just want to update a piece, of course I can use higher order for that. Huh? But you don't want to use this for updating the whole system, because basically you can't, if I want to replace this server by something else, I can't, okay? All I can do is change the function. Whereas in the previous approach, I can change the whole structure of the system, okay? So this is a kind of a fine-grained update. So I mention it so that you can see that it's separate, that there's two separate things, okay? Okay, so those are all the primitives. So up to now, I've explained all the primitives. So the spawn, the receive mailbox, the linking, the dynamic code update. Those are all the primitives. And now we'll have a small break, and afterwards, I will tell you how Erlang uses all that to build all the abstractions we need for making robust software. Okay, so now we make a break. Continue now. So now we saw all the primitives that Erlang provides to make robust software. But in fact, I didn't really tell you yet how Erlang organizes it. If you want to write an Erlang application, what do you do? So let me explain now how Erlang organizes writing. So everything before the break was like the low-level primitives, and I explained them because in this course I want you to understand how it works. But now in the second part, I will explain the generic behavior. So Erlang provides packages, or like software packages, which do all the hard work for you, for update and for supervising and so on, okay? So let me explain how that works. So first of all, the Airline philosophy. So Erlang, people like to talk about this, and I think it's important because it gives you a kind of idea. The question, how do you make software robust? And it turns out, most popular languages, Java, Python, they don't really give you the right primitives for that. And so Erlang started from that idea. How do we make software robust? And they really invented these ideas to make robust software. So there's a number of principles. So this comes from Joe Armstrong's PhD thesis. So Joe Armstrong is one of the key developers of Erlang, and in 1986 and after. And in 2003, he said, maybe I want to get a PhD. So he wrote down all his ideas, and he made a PhD defense from that, and he got his PhD from KTH. And actually, I know this very well because I was on his PhD jury, okay, in 2003. So this thesis explains very well. Errors, so the first principle, you cannot eliminate all errors. So you have to handle them. So the principle is, no matter how hard you try, you cannot get rid of all errors. There will always be errors that exist, both hardware and software errors. And you have to handle them. So building software that is 100% perfect is a utopia. It cannot be done. There will always be errors. That's the principle. So you must handle them. That's the first principle. Second principle, you have to have what are units of failure. So if I have a big system made out of different parts, what can fail? What is the unit? What is the smallest box that can fail? And in Erlang, these boxes are actually pretty big. These components in Erlang, it's not processes. Because of linking, it can actually be a big part of the system. And when one of these boxes fails, the others are not affected, okay? So no sharing, okay? There's strong isolation among the failures. That's the second principle. The third principle, fail fast. When something goes wrong, you immediately fail. Don't try to keep going, okay? Just fail. Fail fast. Either you function correctly or you stop, okay? Nothing in between. Fourth principle, you have to be able to detect the failure. The linking does that. And no sharing. Okay, this is actually related to strong isolation. But even in the low level, no sharing of data structures. The software components don't share anything. You only send messages that are copied. Okay? Now, people will immediately complain, wow, this is slow, etc. You have to do so much copying. But actually, that's not true. If you really look at it, this does not affect so much the efficiency. Okay? So there's some slogans that actually kind of summarize this. The most famous slogan of Erlang is, let it crash. Okay? Instead of trying to fix things, let it crash. So what does that mean? When things start going wrong, the system goes into some complicated failure state when things are kind of messy and blah. In Erlang we say, don't do that. Map everything to one simple failed state, crashed. So anytime something goes wrong, don't try to keep going with a partially correct state. Just make the whole thing crash. Let it crash. Okay? And the second principle is let some other process do the error recovery. So you have one piece of code doing the work and another piece of code doing the error recovery, doing the fault tolerance. Two separate pieces of code. It should not be the same one. Okay, there's a really nice example of this that I like to explain, which is a real story. So this happened some decades ago when there was, in the Soviet Union, it still existed, and they had a base in Antarctica, okay, and there was a surgeon there, one doctor who was a surgeon, but other scientists, and the doctor had an appendicitis, but there was no other doctor. So how did he solve that? He basically operated on himself. And this is a famous story, you can find this. He informed all of the nurses and everything what to do. He installed himself in the operating table with mirrors, so he was awake. It was local anesthesia. And he basically cut himself open and removed his appendix on himself. That's amazing, isn't it? The guy is a real badass, huh? And he survived, okay, this guy. And basically, all of the nurses, he would tell them what to do. And he had mirrors, so he could see what he was doing. Isn't that amazing? You don't want to do that, okay? This is very exceptional. Well, the same thing is true for software. Okay? If something goes wrong in the software should not try to repair itself. Some other piece of software should repair it. So the normal way is if I have an appendicitis, there is a doctor, a surgeon standing next to me who does not have appendicitis and who fixes me, okay? That is the normal, correct way and has the highest chance of success. Okay? Of course, in Antarctica, they didn't have any other possibility, so they were forced to do this. But that's not what you should be doing normally, okay? So that's kind of I think that's a good story, huh? Some other process should do the error recovery. And Erlang follows that, which we will see. A third principle is do not program defensively. So defensive programming is this whole thing where you're adding tests, checks. When you call a function, you check to see that the arguments are good. Whenever you do that, when you return something, you return a code to see whether it's good. So there's checks everywhere, and if statements, and checks and checks. This makes the program complicated. And this, of course, will not remove all errors. So the Erlang idea is this is fundamentally wrong. Don't do this. Don't do defensive programming, okay? And the advantage of not doing it is your program is actually a lot simpler. And if there are errors, just crash. Don't try to do any kind of check or testing or fixing the state. Just crash, okay? A single fault state. So no defensive programming, okay? Okay, so how does Erlang implement this? Okay, this is really interesting. An Erlang OTP. So the platform, when you download it, is called OTP, and it has a whole bunch of libraries in there. It's actually a hierarchy. So the lowest level is the worker. This is a process that's doing something, okay? And the next level is called the behavior. This is like a concurrency pattern. A behavior is like a generic thing, a server, a generic finite state machine, a generic event handler, a generic supervisor, which is the fault handling. So this is the generic pattern, and it's actually a concurrency pattern. Higher than that is the application. This is all the software necessary to run an application, and higher than that is the release, the whole release of the system. So you have this hierarchy. So when I write an application, it consists of behaviors, and the behavior has workers that are instances of behaviors, okay? So this behavior concept is really the key idea, okay? The behaviors abstracts everything out. So we saw before the break, you have linking for failure, you have dynamic code update, you have this receive statement, out of order receive, you have the spawn, and so on. That's all very low level. Usually the programmers don't do that. They use behaviors, okay? And it's the behavior that does all the tricky code. Okay? So basically when I write my application, there's hard parts, difficult parts, and easy parts. So the hard part is concurrency, fault tolerance, code update, and all of that has to work together. That's tricky and hard, okay? And so that has to be written by expert programmers. And then there's the easy part, which is the functionality of the server. Maybe the server will just be doing database query. Maybe I'm just ordering something from Amazon. It's just a business logic. So that's kind of the easy part. I know that that part is not so hard. So that one can be written by regular programmers. So what does Erlang do? Erlang separates that out. All the hard stuff is written in these generic components called behaviors. All the concurrency, fault tolerance, code update stuff, and startup, whatever. All of the difficult is inside the behaviors. And then all you have to do is fill in the function that gives you the functionality. So they're like programming patterns for robust concurrent programs. That's why it's actually very easy to write a robust program in Erlang, okay? It's very easy. You don't have to be an expert in concurrency and fault tolerance to use all what I just told you before, huh? Because it's all hidden inside the behaviors, okay? Okay, and so there's library support. So all of this is in the documentation, of course, so there's piles of documentation and examples, but I won't go into that. So the standard, so Erlang system has 5 standard behaviors that are like libraries, generic libraries where you fill in the blanks. There's generic server, generic event handler, generic finite state machine, application, and supervisor. That's it. Okay? And they have special names. So gen server, gen event, gen FSM, etc. So that if I want to do client server on Amazon, I will use the gen server and I will instantiate it. I will put in my functionality. But all of the stuff, registration, start, stop, timeout, statement, and all the error handling, everything is handled inside the pattern. You see the idea? If I want to do event handlers, so there's streams of events coming in. User interface events, network events. Maybe I'm looking at a real-time system where there's like all kinds of real-world events, and I want to handle them. I want to sometimes send notifications, I want to log them, do certain things. Well, I use the event handler. And if I want to change things, I just call the event handler. I never have to do linking by myself directly or code update or anything. And then the actual functionality of the application. What computation is the application doing? That's actually a finite state machine, okay? So the state is like all the values of the variables, and when the application does a computation, the state changes. So that's the general way any application works, okay? And in Erlang you have a gen FSM, which handles that, where you can put any kind of code in there, and you can update the code, and you can supervise it, and And then application is combining all the pieces into one thing, which is the application. Because maybe you have several of these other guys sitting there together, so you combine them into a unit that can be started and stopped as one thing, and can be reused. So it's like a box, application behavior. And the final one is supervisor. This is for fault tolerance, okay? So these 5 behaviors will hide the complexity. Concurrency, fault tolerance become very simple, okay? And all of these behaviors are designed to be plugged into a supervisor. It's all made to be used together. These 4 behaviors are designed all to be supervised by a supervisor handling the fault tolerance. So it's built into it. You can see it was a lot of work building these things, huh? So the Erlang team spent years polishing and making this stuff work. But now that's done. It's there and it works. And if I want to build a robust, concurrent, fault-tolerant application in Erlang, it's very easy. I just use behavior, okay? Okay, so one thing I have not mentioned yet is the stable storage. So I have a supervisor looking at what the workers doing the work, and workers are sometimes failing and restarting and whatever, the supervisor is observing that. How do you, when you restart something, how do you restart it in a consistent state? When you restart a system, you have to restart it in a consistent state. And the only way to do that is to have a stable storage, which is like a database. And a database with transactions is providing that. Okay? But that's already complicated. So Erlang has different levels of stable storage. So the 2 pillars, the 2 pieces of Erlang's robustness, resilience, is supervisor tree and stable storage. So the supervisor tree observes your system, says when you need to restart, and the stable storage gives you the consistent state, so you can restart. Okay? So those are the 2 pillars of it. And Erlang has 3 levels of that. So the ETS, which is just in memory, they're exact variables that you can update, except they're stable. Okay? You have disk-based ETS. Okay? But this ETS is in memory. So if the memory crashes, it disappears. But DEX is on disk. So these are like very simple databases, okay? Because you don't need full transactions. Erlang also has a full transactional database. Sometimes you want transactions. This is called Amnesia. And this lets you do transactions using any kind of Erlang data structures. But of course it's much slower. So ETS is very fast. Huh? It's like updating a variable, only it's stable. And transactional database, of course, is going to be slower. So there's a trade-off. So Erlang provides you the different levels that you need, okay? Sometimes you need full transactions, but sometimes you don't. Sometimes you just need to store a simple name structure in the stable storage, and that's it. Okay? And the X can be updated very, very, very fast. So it's very high performance. Okay. So that's the second piece. Supervisor tree and stable storage. Okay? One other thing I want to mention is testing. So Erlang has a lot of testing tools. Okay? So of course, all systems that you want to build realistic large applications that need testing. So Erlang has a whole spectrum of testing tools. So unit testing. So you have done unit testing, right, in other courses, I hope. So this lets you do test generators, scaffolding. Also a system testing framework. So you can do running tests in parallel random order for test race conditions, or handling dependencies. So you're basically running a lot of things together. Simulating abnormal termination. So fault injection is very important. You actually run the system and you force a piece of it to fail to test the fault tolerance. It's called fault injection. Okay? And then you have tools, and then one of the tools is called dialyzer. So this is actually a dynamic type checker. It actually can find complicated errors in the types, okay? So this goes a little bit beyond it actually is smarter than a normal, a typical kind of static typer, because it's based on how the program executes, okay? So this is a useful tool. So this gives you the tests that you can do, okay? And now let me show you, I want to show you two things. The generic server and the supervisor. I want to show you how they're built. Okay? So normally you will not build them. You will use the GenServe that exists. But in this course, I want you to understand how they work. Okay? So we're going to construct a simple GenServe. And it's like a design pattern, but it's a library, okay? It's a library, generic library. But it's like it looks sort of like a design pattern. You use it in a certain way, and it lets you build a concurrent multi-agent system. Okay? So these are the OTP behaviors. And like I said, all the tricky things, borderline conditions, are abstracted away. They're all inside the behavior. So now let's do the server. Okay? Okay, I want to do piece by piece. So I start with a very simple Erlang process loop. So a kind of very simple server. How does it work? Okay, so we like this. I spawn the server. Okay, and with this init function, I have some initial state, and then I run the loop. So loop is this recursive function, and it receives requests that we have to handle. So here's a tuple, handle message, and new state. It calls handle on message and the state, and then it goes to the new state. So this is, you can see this is very similar to port object, and so this is basically just doing one message after the other. It's very simple server. So this is the server. I want to split this code into two parts. The part that does the work, and the part that handles all the server stuff. Okay? There's also here, notice there's a stop message, which will do some kind of termination, and it will clean up, it will do something. So this is a kind of simple server, and you can see it looks a lot like a port object, huh? So how do we split it so that on one side you have this generic thing, and the other side you have just the functionality? Okay? So we want the generic part, the GenServe, and we want a specific part. So generic part, spawning, storing data, how you do the sends, how you get the replies, receiving replies, stopping. This is very simple, huh? In a real one, you would also have fault tolerance or update, okay? Redundancy, okay, this is very simple. And then the specific part would be, okay, the server state, what is the loop data, How do you handle the client request? So the function, what is the content of the reply? So the basic data for our application, okay? Okay, so how are we going to do this? So we're going to split this code. So this code, I'm going to split this code into two modules. A behavior module, this is the generic one, and a callback module for the one that the programmer does. And there will be a callback API, and they will kind of agree, okay? So that means when I need to write a server, I only have to write the callback. The behavior will be the same for all servers. Okay? So this is code reuse, standardized, fewer bugs, and this can do all kinds of stuff. This server, this behavior model can do statistics, it can do profiling, it can do tracing, logs, supervisor, whatever. It can do all kinds of stuff, and the callback does not have to change. So it's really nice to do like this. Okay. So I want to do that, but let me do an example. So this example actually comes from the book by Francesco Cesarini and Steve Vinoski. So the figure comes from there. I want to do a frequency allocator. So here's my server, and here's clients. So these are little Erlang processes. This is an Erlang process. And this server knows which frequencies are used by the phones, 10, 11, 12, whatever, the channels. So when a phone needs to make a call, it needs a frequency. So it asks the server, please allocate a frequency, and the server says, you can use frequency 10. Okay? And another phone can say, I want a frequency, it uses frequency 11. And the server keeps track of which frequencies are being used. Okay? So it's just like a simple database, actually, yeah? And then when the phone is done, it says, I don't need this frequency anymore, deallocate it. And the server says, okay, the frequency is free again. And then it gives a confirmation, and then some other phone can use that. Okay? So when a phone needs a frequency, it asks the server, please tell me what is a free channel. And then the client, so the phone, holds the frequency. When the call is done, it deallocates. Okay? So these are all Erlang processes. So there's like a simple data structure here, and you do allocate and deallocate calls. Okay? So this is kind of example from telecom. Huh? So this is the API for this. When I'm a client, okay, when I want a frequency, I call allocate, and so this is a specification. Huh? This is not code. Huh? When I do allocate, either I get a frequency, so I get a tuple saying, okay, and here's the frequency. So this is a variable, there'll be some number here. Or I get a tuple saying error, there's no frequency. Maybe there's too many phones. And if I deallocate a frequency and it just returns okay. So this is basically the API. Yeah? See how this works? It's not the actual code. Huh? And I also have start and stop. So I can start the frequency server and I can stop it. And internally, the frequency server keeps a data structure. So basically, it keeps like a set of frequencies or a list, okay? 10, 11, 12, 13, 14, 15. So these are all the ones that are free, and these are all the ones that are allocated. So if I allocate frequency 10, then the free tuple becomes this. The 10 is removed here, and it's added here. So basically, it just keeps track of which frequency is free and not. Okay, so this is very simple. I'm just defining this so that we have an example for the Gen server. Okay. So I start the frequency server. I can allocate frequencies. Upon each time I call allocate, I get another one. Okay. If I allocate 6 of them, so these are normally going to be 6 different phones allocating them. Huh? This is the Airline top-level interface. Huh? You can do interactive messages. So I allocate 6 frequencies, and the last one, this is the last one I get, which is 15. Okay, so I'm assuming there's 6 frequencies, 10, 11, 12, 13, 14, 15. So I allocate all 6 of them, 6 calls. If I try to allocate a 7th one here, it says error. Okay, if I now deallocate 11, I say I don't need 11 anymore. 11 is free. If I allocate again, it'll tell me 11. Okay, so it just keeps track of which ones are free and not. And here, if I stop, then it's done. Okay, so this is how the phones are going to use it. This is an example where I'm doing it interactively, yeah? But these calls will be done by the phones. They allocate. See how it works? Do you understand that? It's not a complicated thing, huh? It's just managing this data structure. Because this is going to be my example. Okay. Now I want to, let me show you the architecture. I'm going to show you 2 modules. This module, this blue module, is what the programmer writes. Okay? And this blue module is part of the system. So this is the behavior. Okay? So the programmer only has to write this, and basically, it has an API. Just allocate, deallocate, start, stop. And this generic module has 3 interface, start, stop, and a generic call. And it will do callbacks. Init, handle, and terminate, which are implemented here. Okay? So I only have to write these 3 things, init, handle, and terminate. All of the work of the actual server stuff is done here. Okay? So that's the structure. And this one, so I only have to write this, but this one can be very complicated. Huh? I'm going to show a simple one, but in real life, this one can be fault tolerant, it can do updates, it can do logging, it can do profiling, whatever, auditing, it can do all kinds of stuff without changing this. Okay? So this is a very nice generic thing. Huh? So the frequency module looks like this. Okay? So it's basically, so this is a module, frequency. This is the interface. So this is what the phones will do. Start, stop, allocate, deallocate. Okay? And there's also a callback interface. Init, terminate, and handle. So the generic module will call these 3 things. So init to start, so it's this, huh? So it's basically a tuple of 2 lists. Terminate, which in this case is not doing anything. And then handle, which does all the computation. When I do allocate, or deallocate, so when I do allocate, I call this function allocate, which does this list. So this is list thing, huh? It's going to take an element of this list, return it here, and remove it from the free lists, okay? So this is just list operation, and deallocate is going to do the opposite thing, okay? So that this is the code actually doing the computation, this is the interface from the server, and this is, I'm calling the server. So interface, interface, and computation, okay? So that's all I have to write. It looks like a lot, but in fact this is like boilerplate, doesn't change. And these things are just, the server will always need that, init, terminate, and handle, okay? And then the real work is done here, okay? So that's the frequency module, what the programmer writes. And now the generic server module, it has start, stop, and call. So start, stop, and call. Okay? So start will spawn the server and register it to the name. Call will call the server and receive the reply. Okay? Basically, it goes through the loop here. So this is like an RPC. Yeah? I send and I receive. So I'm doing round trip here. And stop will stop everything, okay? And then the actual server is here. Notice the 3 red things are the callbacks. Init, handle and terminate. It's always like that. Huh? So this is like fixed code. The loop is receiving a request here. It's going to do the handle. It's going to call handle. And then it's going to reply. So this comes back here. And then there's terminate and there's init. Okay? So this is a very simple one, huh? Because it's only doing the loop here, huh? But of course, Railgen server is going to do much, much more. Okay? So you see how it works, huh? You have these, I'm splitting into two modules. So the organization is this. So the server will always call init, handle, and terminate. So this is the callback interface. The server interface is fixed also. It's always start, stop, and call. And then I make my external interface, and I will call the server interface, and any computation that I have to do is here. So the programmer will only write this part. Okay? So you see how it works, huh? How you can build a generic server. So this is a very simple one, huh? You see? Do you understand how it works? So you have to, so I expect you to understand this code, huh? To be able to read this. It's not so complicated. It's very similar to ours, except with slightly different syntax. So parts of this are fixed. Start, stop, call, init, terminate, handle, and then this is the actual computation, okay? So the part of this is fixed, always fixed, huh? So the callback interface and the server interface are fixed, and it's part of this thing, okay? See how it works? So that's a simple generic gen server. Okay, so that's a simple behavior, and the real Erlang behavior, of course, is doing much more there. Okay, right? It's good, right? You like it? So this is Erlang. Okay, now we don't have so much time, but I want to also show you the supervisor. But so maybe I will just introduce. So the other example I want to show you is a generic supervisor. Now, the code is also not so complicated. It's one page. It's one page of code. But supervisor is a new thing, which you have not seen before. Whereas server is something you know, okay? So even though the code is only one page, it's it's new code. So it'll take maybe a little bit more effort to really understand how it works. So I'm not going to show the code, but I want to show you the ideas of the code, and then we look at the code next week. Okay? So supervisor trees. So what's the idea? So I have a system that's running. And one observation is most errors are transient. Network problems, dropped packets, timing problems, concurrent startup, out of order. So simply retrying is a successful strategy. So the supervisor tree, it can do anything, the supervisor. But actually, it's designed to start by just doing simple retry. And actually, that solves already a lot of problems, okay? So supervisor trees are designed to favor simple retrying, okay? So you have a set of processes that are doing the work, applications running, and they're all linked to these supervisor processes. They're linked using the linking we saw. And the supervisors have authority, so they can stop and restart these supervised processes. They can restart the whole system. Okay? And what's really interesting is that very often you have two layers of it. So the supervisors, what happens if they fail? Who is going to guard the guardians? You know that expression? If the guardians are making sure the laws are obeyed, who is guarding the guardians? Which is a famous phrase coming from antiquity. Well, who is going to fix the supervisors? Well, you have a second layer of supervisors. So basically it's a tree. So it kind of looks like this, if I make a picture. So I have worker nodes here. So these are workers. And here I have some supervisor nodes. And they will observe all the workers, okay? And on top of that, I have another layer of supervisors. So this is the high-level supervisor. And usually this one is very simple. Okay? These middle supervisors can be actually quite complicated, huh? Because they are handling all of the failure techniques, and this is the application, huh? So typically, this high-level supervisor is extremely simple, and so simple that it's almost never going to crash. Okay, this one will not crash. Okay, so usually the Erlang will be written like this. So the AXD301, this actually has two-level supervisor trees. Okay, so that's how it works. And these supervisor trees, so this layer here is the code is not so simple. It's very careful to avoid race conditions. Especially when you start up the system, you have to start things up in the right order. So it's kind of tricky, but that's okay because it's inside the behavior. Okay? So just a few words on the principle. So the supervisor tree is a hierarchy with a root. There's a set of supervisor nodes, and there's internal nodes. And each node observes the nodes that are below it, the child nodes. Okay? And it has some simple principles. There are actually 3 or 4 simple restart strategies. Okay, so the main ones are 1 for 1 and 1 for all. So if the supervisor is observing a bunch of nodes, if one of them crashes, there's basically 2 possibilities. It restarts that one, the retry, or it restarts everybody. And it depends on whether the nodes are doing independent tasks or whether they're working together. If the nodes are working together, maybe it's like a big logical thing where they're all implementing business logic or something, then you do 1 for all. If one of those nodes crashes, you restart all of them in a consistent state. Whereas if the nodes are doing independent thing, like telephone, each one is implementing 1 phone connection. Well, if 1 phone connection crashes, the others keep running. So you only restart that one. So the 2 basic ones are 1 for 1 and 1 for all. And then you have variations, which I will explain later, rest for 1 and simple 1 for 1. Okay? So the basic strategy is just restart by default. Of course, you can do more, huh? You can make it more complicated, but the by default is following this principle. Most faults and errors are transient, so the basic by default strategy is just a restart in a consistent state. Okay? That actually solves many problems, but of course, it's not enough. The number of restarts is limited. Sometimes you will keep restarting. It keeps failing in the same way. Okay? It dies repeatedly for the same reason. Well, that's why there's a limited number of restarts. And if that limit is exceeded, the supervisor that does the restart is terminated, and a higher level supervisor will say, aha, this error is happening over again. We can't just restart, we have to do something else. Okay? Maybe one of the processors is really failed, or maybe there's a disk crash and we can't use this disk anymore, maybe we have to reconfigure the whole application, okay? So that has to be done at a higher level, okay? So that gives you this hierarchy. So here you have, these circles are the worker nodes, and then these boxes are the supervisor nodes. Here I'm looking at only one for all and one for one. So the two basic strategies. So you can see it works because the default strategies are simple. You might say, how can this work, this supervisor idea, because the system can fail weird ways. But it turns out that that's not true. The system is going to fail in simple ways, and almost always you can use just one of these two strategies. And in those cases when it doesn't work, you can do more, but you only have to worry about that in that particular case. Okay? Okay, so let me stop here, and next week I'll show you the code for this, and you'll see how Erlang does the magic. Okay, so let me stop here. I think we're at 10:30. Okay.